Почему? Ну это просто магия. Почему по умолчанию должна...
Так, у вас уже трансляция запущена? Нет, там всегда говорили, что надо сбрасывать на умолчание. Звук работает, если что. Начать запись начинать нажимать не надо, так YouTube сам записывается, уже через него транслируется. Вот тут у нас стримится. Сейчас. Пошло? Никто не смотрит, правда, кроме меня, поэтому если там звук не записывается, это в последний момент узнаю.
Okay, so in previous class we have proved the following. So suppose we have G, a fine algebraic element. And H is a subgroup, algebraic subgroup. Then we have done the following, so we have then, so this is theorem of Chevalier, embedding theorem. So that there exists the following, so there is a homomorphism of G to some linear group active on vector space, and so G acts on V linearly. And then you have the following thing that there exists a vector in V such that H is precisely the stabilizer of the line spanned by the vector. So the stabilizer in G of the line spanned by this vector where V is the element of projective space. So then we want to derive out of this, which will be non-trivial, but this will be corollary of this theorem, or at least it will be proved as the corollary, that if you have a normal subgroup, so if H is algebraic normal subgroup, algebraic subgroup which is normal, then G mod H is also, so it is of course a group, but it is algebraic, well, a fine algebraic group. Yeah, so again, well, why doesn't this follow from this? Because simply it can happen, so let me put an example of, so at least it won't be example to this, counter-example to this proposition, but this is example that this G mod H is not always affine, so just G mod H can be not affine. And the reason for this is that you can just consider the tautological SL2 action on K2. that this is matrices, and they act on the collection of vectors just by multiplying, just like the linear operators. And here you, if you look at projectivization, yeah, so here there are quite many examples related with this thing. So, for example, what are orbits? Yeah, so what are orbits of SL2 and K2? So you can specify two orbits. Yeah?
0 and
Zero and any other orbit. Yeah, so zero orbit has stabilizer, which is equal to SL2, but the other is just K star without zero form one orbit. Because it is just mapping a vector to any other vector, non-zero vector via general transformation. And notice that stabilizer, so you can calculate the stabilizer of the vector, and the stabilizer of the vector in G is just what? So what matrices? First vector maps, I mean it can be put to be basic vector.
because they are both
Without loss of generality. Yeah? So because of transitivity, this is called transitivity of the action, when any vector can get any non-zero vector can get via this action. So and this means that here you put 1, so it is identical on this vector. So I'm writing down images in the columns, and here I can put any vector. But you are picking up SL2, yeah, so the determinant is 1. So here you know that it is definitely 1. So this is called actually a maximal unipotent group, if just for SL2. But we shall discuss it a little bit later, what it is. So at least what you see here, that it is just additive group. If you multiply such matrices, this number will be added. So this is just isomorphic to K plus.
What is this word? Unimportant.
Unipotent. Unipotent. So maximal means that it is, you cannot find, so it is maximal not in the sense of groups, because trivially you can embed this in triangular matrices at least. But this is maximal as being with a property of being unipotent. Yes, so maybe we can state what is unipotent. So just X. Well, operator is called linear operator in GLV is called unipotent. If you subtract unit, it becomes nilpotent. So if 1 minus A is nilpotent, you know actually that in matrices you can find it. Yeah, so if so this is the stabilizer, and you see that the quotient modulo, so this letter is denoted by U. So SL2 modulo U is just isomorphic to K star without 0. And notice that so sometimes open subsets can be affine. Yes, so if you pass to the complement to the hypersurface, as we learned, it is just affine space, and we have realized that it is a closed subset. But this is not so K star without 0 is not affine.
K squared, not K star.
Yeah, k square is not affine.
The quotient is this because it's not expressed, it's an orbit.
Yeah, it is
That's
just
right.
an orbit. It is full orbit of SO2 acting on this space. And so we have learned, I mean, for the orbit, we know that there is orbit morphism of, and the orbit is isomorphic to G mod stabilizer. And so that it is a particular example of just what we're doing here, but we have proved that this is equivalent. But I want to notice that this is not affine, and it is not complicated exercise, and it is related with the following. So affine varieties are characterized by, affine varieties, as we have learned, are characterized by their algebra of functions, algebra of regular functions, and you can calculate the algebra of regular functions. Yes, so you and you notice that so this is calculation. So that algebra of functions on this set is just the same as the algebra of functions on k squared. So if you have I can maybe I should write k2. Not to make the notation too ugly. Yeah, so you see that, but since the affine varieties, you have already one affine variety with this algebra, this is definitely not affine.
So, should we stop you if you are writing very strange words on board, like way you write you should
Characterized.
and first CH.
Okay. So, so this is not a affine variety, and just for the reason that its algebra of functions is equal to the algebra of functions of affine varieties, and they are not equal. One is contained in the other. And this means that you see that you have just to calculate the following. So you just so for example you can then this is calculated as follows. So that we didn't say what is but let us notice that if you have x which is covered by affine charts, so just k of x is formed by the functions f from topological space to k such that the restrictions to ui are regular functions, are regular on this affine chart. And what you have to do when you calculate this, you have to cover this by the evident charts and understand how they. So of course, fi should be equal to one function in the end of the day. Yes, so it should be. So this data is of course consistent. So consistency of this data implies that this is just polynomial.
This means that we have like one particular map, like embedding A2 without 0 to A2.
Yes.
Which is like isomorphic.
Yeah, so if it was the map, yeah, so I mean to say it even better, I mean, of course, it is. When I'm saying that the affine varieties are characterized by KFX, yes, so this is not all, of course. I mean, this is not saying that you just have an algebra and then you are done. You also have to prove that this guy is not equal to this guy.
Yes, you say it's not equal because it's embedded, but
yeah, but this if they are embedded, then this means the following. So if you have just if this embedding is a regular map, yeah. So for example, you can see the following. You can just write. So here, if you write down any line, it a fine line has. So this has the affine lines that are just they are on the they just the lines, and here you have the lines without zero, so you can distinguish this object since you can draw here the line without zero. So if you know that this object is not equal to this one, so saying that the affine varieties are characterized,
I can write without zero in A2.
you cannot write down the line without zero in A2. I mean as a closed subset. And here you can. So, so this is just what I want. And there are other examples even better. So the varieties which are open subsets of affine varieties are called quasi-affine. And then also you can do the following, so you can consider the action of SL2 on projectivization of this vector space K2. And here, of course, the stabilizer becomes the following, so you can take a vector here. So so here we are speaking about now stabilizer of the line. So I pick a vector and the corresponding line that's spanned by this vector. And the stabilizer in SL2 is just what? It is the group that acts on this vector by the scalars, by some, so it can map the vector to proportional. So, this is precisely the following. So you just the first vector can map to proportional ones. So this means that I am putting higher p here, so which is a number. I just want to say that this is some number. Yeah? So let it be just the big matrix. And this is some number, lambda, so I consider the following matrix of this form. And when you are looking at projective space, here you can map any line to any line. So this acts transitively, and you see that it is not affine, but from the viewpoint of our homogeneous space, it is a SL2 module of this group. So you see that this explains why this proposition somehow is non-trivial. So you have to use somehow that this group is normal. I mean, if you were satisfied like having in the end of the day just algebraic groups, then but actually just one can derive this by final analysis, which is useful on its own.
So is it so that stabilizer virtually is not a normal subgroup?
Yes, I mean even for finite group.
But we take stabilizer not for like for the vector itself in this example.
In which example? Here.
Yeah.
I mean, well, it is even better. It shows that even knowing that I can put it, I mean, if I know that the G mod H can be realized as a stabilizer of the vector, it doesn't also imply that the homogeneous space, so this theorem doesn't say that the homogeneous space is affine, it could be quasi-affine.
I think there should be a lambda inverse.
Yes.
Where? I mean, here?
Yeah.
Not here.
In matrix.
In matrix.
Yes, just I thought that, yes, sure. So, yeah, so yeah, so this shows that the theorem is still non-trivial even if you avoid this projective space. Yeah, so that your stabilizer can be the stabilizer of the vector, but it can happen that it can happen that it is the stabilizer of the vector, but it can happen that this is not a fine variety. And also, if you just here we're speaking about V, so the vector and projective space. Of course, if you have already embedding an affine space, so V embeds into projective space of V plus 1. So V plus 1 dimensional space. And you may think as just the group is acting on V, and you can think of the trivial linear transformations on K, so this allows you to embed, even if you have a fine embedding, this shows that you can also have, you can construct the corresponding projector. So, yeah, so let us move to proving that H is normal. Yeah, so when H is normal, the situation is better. So, what you know, what is the starting point? The starting point is the following, that you start by, H is acting on V, and you know that just for the vector V, the action of H is acts by some character. So since it is it's simply just this is the notation of the vector, so this shows that and this is linear map. So this fixed vector and just the line plus linear map. So this gives you that K of chi of H1 and H2 is equal to chi of H1 chi of H2. And so that the linearity of the action shows that this is homomorphic. Of course, I should say that warning. So there are of course actions that are not of this form. So, for example, you can just pick up the coordinate and act by translations. Yeah, so that the matrix of this form. Yeah, so just T maps to X plus T. It will be also an action, but this is not linear action, yeah, because it is a fine action. It can be done linear, but with the price that you add additional dimension. So just saying that this is true, this follows from linearity, and that we have here in the beginning. So,
There's a good sign of this
what?
T upside down. You mean the prefix V and linear map.
And this G acts linearly, and in particular H acts linearly.
But how do you use linearity like?
You just use action, but
So H and Z.
I mean it is just a second. For me, it's easier to write this down. So let us act by H1, H2, and V. So on the one hand, you are acting like H1 times chi of H2 of V. But now we use linearity, so this is scalar, so you can put out, and this act by the method. So you can, it can be written as chi of H2 times H1 of V. And this is now chi of H2, chi of H1. Okay? And I mean, you have to commute the scalar out of this argument, and you cannot do it here.
And please explain again what is x and t in the warning.
What?
What is x and t in the warning?
Yeah, so just here you have k plus, and t is also, so this is a coordinate on k plus, and so on A1, and t is also the element of k plus. And you have an algebraic action of k plus and k plus just by mapping x to the coordinate translation. But the parameter translation varies under this varies if you take different metric. And this can, I mean, I have realized that writing this matrix, I meant that now you can think of this as the follows. So as a picture, yeah? So you can think of this. So you can take. So notice that this, if you look at, this matrix, it acts. So it fixes the point with 0 coordinates on the line y equal to 0, and if you look at the corresponding, if you look at corresponding just line xy, and so the point on the line xy, it will be the first coordinate will be x plus ty. And the second is just y. So the coordinate y is preserved, and this is mapped. I mean, for y you can take 1, for example, and so you see, so y is equal to 1. So you see that this is precisely the translation x plus t, and here you just fix this coordinate. So this is on this line, it is just, it maps x to t plus x. And so this shows, of course, that this is in particular case of the linear action, and but you see that itself, the action itself is not linear corresponding on the corresponding line, affine line. So that's why it is easy, but not completely. I mean, trivial, but it should be not. It can be otherwise. So also what happens? So you can, when you have this kind of situation, it is convenient to consider the space eigenspaces. So these are just the vectors V, such that H acts on V via this corresponding character. So this is, and notice that there would be several such eigenspaces, and so this, and if H is normal, then this Vk are permuted, Vk are permuted via action of G. So via action of G. So this just I shall explain why I'm using the word permuted. Simply as because of the following. So if you have first you notice that vectors with different eigenvalues are linear independent. Yeah? So just let us recall that vectors with different eigenvalues linearly independent. And then we notice that you can take any element of G and apply this element of G on Vk, on the vectors of Vk, and notice that just let us rewrite what does it mean. So let us apply G to V and then try to apply H. So since H is normal, so you know that this can be written as G inverse Hg. So this is times G. So this is an element of H. Then I claim that this is also eigenspace for H, but with different characters. So, and now I want to calculate this character. So, just let me calculate and then I shall state what we are saying. So, I want to do the following calculation. I take the vector from, just take G from V and the V from V card. So I add G times V and then apply H. Then this can be written as G inverse Hg, which is trivial, but now this is an element of H, and this, so you can write it as you apply it to V, and this is a character. Yeah? So this is G times character of G inverse H of G. So thinking of this as so let us, this belongs to H, so it is some H tilde. So that you can think of this as applying character to H tilde and V. So you commute G and V because the action is linear. And you recover that you have to multiply the character via this conjugation.
Do you mean that the eigenspace has the same eigenvalue for all the elements?
No, it will be different. Yes, I mean this for fixed function chi. So I mean we start by fixing the homomorphism of H to K star. Okay? So this is a function that just So it's saying that it is character, so that this satisfies this property simply means that it is homomorphism to multiplicative group. And then given this function, so it is function on H actually. Just it is algebraic function. This is also notice, so there could be quite different homomorphisms, not related with algebraic structure, but since this homomorphism comes from the linear action on the vector space, it is also a regular function. So it is regular function on H, so you can, but anyway, even without saying that it is regular function, so for this function you can consider this vectors, subspace of the vectors that behave as a just multiplying by this function.
Is H not trivial for H or just
For any H. So this shows that so this is like the vectors that behave uniformly with respect to the action of H. And this shows that if you take such a vector and apply G, it will be when you apply H now, it will be multiplied by the different character. So if you put that character K tilde of H, a new character is defined as character of G inverse HG. Notice that this is also a character because it is composition of homomorphism and which is conjugation. So this is actually anti-homomorphism. So conjugation and you apply the character. So it is a character. So claim that we have established that if V of K is eigenspace, then just if you apply G, this will be also the eigenspace of a different character, possibly with different character. It could be the same actually. I mean, if the functions is the same, then you have your just vector space to itself. So in so you know after this you know that you can consider the following object. So in V, so in consider the sum of the vector spaces corresponding to Vk, where chi is different characters of H, and notice that this since vectors of different of different eigenspace are linearly independent, then of course this sum will be direct. Yeah, so this means that since we assume that the functions that are involved here are different as the functions, and so if you have what a linear combination involved, with so you can think of it as a linear combination with maximal number of with minimal number of elements, And of course, there will be a function, so you just can find h that will be a different, that the values of the eigenvectors will be different. Yeah, so that just what I mean that if you have the sum of v chi I, so there exists h such that chi of h is not equal to chi to g of h, and this will give you in the linear combination, you will get the vectors with different eigenvalues, so that is absolute for the action of this given h.
It's not really,
Huh?
it's not really that easy. So there is like a big sum, like it's one of.
Yeah, I mean, there is just
Some with coefficients, yes?
yeah, I mean, you do not have to involve here coefficients because these are just the vectors.
Some vectors. Okay,
Some vectors with different eigenvalues.
so we have.
You just want to understand that they are, so this sum should be 0.
Yes.
But this sum depends on when you apply h to this. And so when you apply h to this
So
sum,
yes, if you can find h and if we apply such h, we get non-zero vectors.
you get the corresponding linear combination.
Yeah.
Yes. So I claim that now I can subtract, as in the proof of the just linear independence, just I can take this just to be true. Yeah? So for some chi I, you will have this inequality. So for some element of h, just because chi I are different functions. And you multiply this, yeah, so for example, let us split it with chi1. So I multiply this by chi1 and subtract, yeah? chi1 of h, and subtract. So the first term will be cancelled. And so I is bigger or equal than 2. Yes, so the first term is cancelled, and here you have smaller number of elements.
So it's like vectors with different eigenvalues are linearly independent, even if it's like.
Even if there is a family of these vectors are dependent. So the only difference is just that here a priori it is, these are different functions, and so you have to specify when you are just speaking about the different the eigenvalues, you already have values. So the only step you have to do here is to make them different. So
And for given space, how many characters do we have?
I mean, if you are in this eigenspace, you have only this. Yeah,
So-
я вопрос не понял. По-русски спросите, все ответить.
Что здесь получается одно значение для всей группы?
Ну, не значение, это функция. То есть, как бы вы берете разные h, и тут получаете разные числа. Но вот это функция на h, она сопоставляет элементу h какое-то число.
Она получается не определена все.
В смысле? Она на h, она же не определена, конечно. Да. Yeah, so there was a question of this function, that this function of course depends on h, and it is not defined on the whole group G. Yes? So the reason that we can write it down here is that this is an element of H. So this you can calculate it as an element chi of H tilde, but H tilde is different element not equal to H. Yes? So this is this H tilde that we have written.
And the great section can continue or character in the whole group or can't.
But it's not a character. I mean, for the whole group, it's not a character. You cannot evaluate. Yes. I mean, yes. You just. But no. The answer is no, because if you are saying that, so you simply can write a different character of H. So the problem is that if you so what is written here is G inverse HG. But if you are saying that you want to evaluate this character, so this is evaluation on H. But saying that it can be extended to the whole G, so saying that you can evaluate it on G tilde, but you cannot evaluate this on G tilde because this will be just a relation to evaluate on G tilde this function. You are writing down this one, and this is an element of G where you are not defining you cannot define your action. Да.
Вот смотрите, там иксы-то все равно ноль, это почему? Плохие-то.
Ну, в смысле, пусть они линейно зависимы.
Yeah,
So if this function, so let me write it explicitly. If this is not, so if this not equality, then there exists a linear combination. So a vector V, which is linear combination, zero vector. So if I equal to 0. Yeah, so if it is not the direct sum, so you can map to the direct sum and get a vector which is 0. So if it is 0, then you just can apply an element. So this is just applying H to this vector V, and this is still equal to 0, but you can just, so this is H. This is H. So if it is E, then this is just H. And this is V multiplied by H. So just chi 1 of H minus H of V.
So by conjugation we obtain new characters.
Yes, we obtain the new character on the on your group H, but it's not the character.
And choosing collection of characters is equivalent of choosing some elements G1, Gk, such that each of them can be.
No, there could be different characters that they are not functions.
Characters additive.
What?
Can I add to it characters and get one more?
So here the problem that first of all it is homomorphism. Yeah, so this it is homomorphism on multiplicative group. So you can. I mean, these are not characters of representations which of finite groups. I mean, so the problem is that some words in mathematics are overloaded with sense, and this is one of them. I'm sorry. So characters now play, so these characters play a role as the homomorphism to multiplicative.
А эти морфизмы образуют какую-нибудь смесь? Как они все выглядят?
Ну, как бы, yes, So if so there was a question how these homomorphisms are defined, and this of course should follow from the following observation that if you have the map from H to abelian group, so this is abelian. And so we know that this factors through commutant, the commutant of H maps to 0. So this factors through commutant. And then the question, simply all such phi are permitted. So now you have simply two abelian groups. And so you are asking about what are possible forms of this abelian group, or more specifically, you are taking for this abelian group, you are putting the K star. But so the question is how complicated can be a abelian algebraic group, and we shall discuss this a little bit later, so it will be just, over algebraically closed field, if you forget about connected component, so let us put H tilde, so H tilde in for K equal to K bar is just the product of multiplicative groups and the additive groups. So it is just a product of K plus in some power n times the product of K star in some power n. So it is quite easy, and it shows that, so there is a good exercise. Maybe since I have mentioned it, so we have to do it now.
This is some G or some
Arbitrary. For describing characters, you do not have to do it. The characters as abstract characters.
You mean that after factoring my commutator, we are left with additive and multiplicative one-dimensional groups?
Yeah, in some power. So the just characters which are maps of algebraic groups will be quite easy, and the reason for this, can I erase this? Just so proposition, there are no homomorphisms. And actually maps, algebraic morphisms. Yes, so there are no homomorphisms in between multiplicative group and additive.
You mean as algebraic?
As algebraic groups. So the thing is that of course you have inclusion of A1 without 0.
So we have like maps like in groups and as algebraic varieties, but not as algebraic groups.
We have a map. Yes, you have the only map that you have between these groups as the maps of algebraic varieties. It is the map of without the group structure of algebraic varieties. And also, also you have, of course, exponent map, but it is not in our category. So the exponent map that maps K plus to K star. So this, you can of course write this down, but this the problem is that you have to calculate the series. I mean, even if you can divide by n factorial, so the characteristic is not just p. So this map is this map is not algebraic, so not algebraic. So this is actually the problem and the benefit. So the problem, this is problem in Lie groups that really tells you that when you're in the category of Lie groups, it becomes a little bit more complicated because this map exists. And in our category, we simply do not have the maps between these groups and homomorphism between these groups. And this allows you to say something about the group structure. So, for example, you do not have actually the maps. There are no maps from A1 to A1 without 0. So no maps like this. So here you do not have even the maps of algebraic varieties.
Everything point.
Well, non-trivial one. I mean, here there is also trivial homomorphism. What is the reason? Do you know? So let us try to look at the rings of functions.
Reducibility.
Well, the reducibility of what?
Of A1 and not
No.
A1 without 0.
They are all both reducible. Yeah, so the thing is that here you have the ring which is formed by. So how to describe this one?
K of x and x minus.
X minus, so precisely. And here you have to map it to. Yeah, so if you have this map in this direction, then you have to map back. Yeah, so this map to this one. Yeah, but what is, for example, so what can be said about this ring and what can be said about this ring? So are there many so what are invertible elements here?
Constants.
So invertible elements are constants.
So we can map x to only two constants.
But it's not bad. Yes. So this is precisely what this. So now this is a map to the point. Yeah. So invertible elements are just constants. So x is invertible.
So x maps to constant, and if our map, like pullbacks, maps map.
So x inverse also maps to constant.
Yeah, and this means that.
But everything maps to constant, and this means that it is an evaluation map. I mean, if you have the map from the ring to constants, then then this is a map simply to the field. Yeah? So this map of k of x inverse maps to k, actually to some constants, but this is a field, so this is a homomorphism to the field. So this is homomorphism. So the kernel of this homomorphism is just a maximal ideal, and this corresponds to the mechanical derivation. So So the inverse is also just not too complex.
I'm sorry, but inverse we have inclusion of algebraic varieties. Why it's clear that there are no
I mean, I have to additional just use that.
So we should use the structure of
yeah, so you should use somehow the structure of groups.
So we can just see that image is constructible set on line, and constructible set on line which is like some type of A1 is only for A1.
Yeah, but also notice that that can be fine. I mean, just if you are saying how many maps of this form, you are not right that there is a unique map.
Yes, is that all these maps like has image like A1 without support?
Yes. And but it is not embedding of A1 without. Because there is a natural map. I mean, it's not just completely evident because you have the map K star that so here you have roots of unity. Okay, so there are roots of unity. The group that consists of psi to the power n is equal to 1. So if you can factorize this by this group. So just quotient by this group as this is finite group. You can take a star and make a quotient. And that is so this will be isomorphic to K star. And from the viewpoint of algebra, it is just mapping so you have to produce the converse map. Yeah? So you can in just K X X inverse, there is at least an algebra generated by the powers. So n powers. And this will be precisely the corresponding, just the corresponding map. So this is isomorphic to the ring of KFY inverse. And
So that is like map multiplication to -1.
yes.
But
I mean, for factorization by -1, saying that here you put squares.
so it's a square root.
Yes. So for this it is squared. But you can take any
And I mean, if we have like k equal r, then we have like square root as this embedded, or what do you say?
what?
If k equal r, like real numbers, then the only root of unity is -1.
Yeah, but the problem is that you think of this as even if you restrict your field to K, the group can be as an algebraic group, but as a set defined by equation, it exists.
I will make an example of map from A1 without 0 to A1.
Yeah, here it is. I mean, it is defined by this inclusion.
Yes, but what is this map? Like point to point.
Find point to point. I mean, well, if you extend the field to algebraic level, then it will be factorization by this subgroup.
So if we have like C,
Otherwise, you can define it by equations. I mean, you can define this map by equations, but this, from your point of view, you will think as if it is bijective map.
so So what will be these equations like if A is equal to property?
Just raising to the power, just raising the coordinate to the
not
power.
square roots. Okay, yes, obviously we can raise to the power.
So the only thing that so you can raise it to the power, but from the viewpoint of R, it will be isomorphic, but it just doesn't mean that.
What? Raising to the power is not isomorphism
For cube,
even for because inverse map is not algebraic.
yes, but I mean it will be bijective. I mean on the set of points it could be bijective, but algebraically, yes, it will be not precisely.
So the claim is only one direction.
So we explained only in one direction, but if you want to explain in the other direction, then you do the following. You describe all the homomorphisms from your group K plus. Yeah, and homomorphism of your group K plus are just K star, are just of the form K star modular. You just say what, you just raise the question, what are homomorphisms of K star, and you prove that they are like this.
All have this form.
Yeah, all have this form.
Okay.
And if of case it's endemorphisms of K star to itself.
Yeah, I mean this is exercise. This is not
It's not
just done the time. So yeah. So what else? Then you know the so notice the following. So I claim the following that just. So you see that if you have V, if you take so in your V, you can consider the set of characters. So now we consider that actually so here we consider specific set of characters, but we can consider just the set of all characters. Of H in K star, and so you see that we have proved that here you have the direct sum formed by this characters where K is arbitrary character of H. And this means since you see that it is a direct sum, so which is defined as the sum, but it is direct. So
It means that the sum is over all characters.
yeah, the sum is over all characters, over infinite set. But
If every character is met in this sum.
But I mean, I didn't say that this is not zero. It could be zero subspace a priori. So, of course, we have, so you see via this, for example, via this property. So, if you make this just claim for granted that the Billion groups are the products of K plus and key star, you see that a priori there can be an infinite number of characters. And but here in our situation, you notice, so you can take all of them and try to take all the sum. But here you see that this sum is direct. So their number of characters is less or equal than dimension of V. Yeah? Since dimensions of you can just bound the dimensions of non-trivial vectors.
Excuse me, why there is a vector in this V corresponding to your check? V is some concrete subspace.
Не понял.
Ну вот у нас есть какие-то абстрактные гомоморфизмы, почему
Да.
каждый из них соответствует
Я же не говорю, что каждому.
set of all checkers.
Ну так
Просто все
вехи могут быть нулевыми. Просто вообще все. Все гомоморфизмы.
А вы это
Нет, так еще раз.
В это вообще говоря любое пространство, но, например, то, с которым мы стартовали.
Ну вот я и говорю, что критерий,
Ну, в нем
векторов может быть много, а векторов соответствующих им вот векторов много.
ну так правильно, ну так я и хочу об этом сказать, что вот этих характеров будет лишь конечное число, а не число не нулевых, характеров, соответствующих нулевым вахитам.
Ага, то есть всего характеров может быть много, а мы считаем только те,
Всего характеров обязательно будет много, потому что даже на К со звездочкой вы можете возводить любую натуральность. So there are infinite the set of such functions is of course infinite. This is infinite even for K star. And a priori this could be infinite set. But so those characters that appear as non-trivial factors, so the number of characters for which is not equal to 0 is finite. It's finite. And bounded by dimension of V. And the number is bounded by dimension of. So this means that the group G acts actually by permutations on this set. So yeah, so the action, so we noticed that G acts on the set of characters. And so here the formula, so G maps chi to the corresponding chi of field of H, defined as G inverse H G. So this gives you a well-defined function on the set, defined action on the set of homomorphisms of H to K star. And notice that we have noticed that G acts on V, and G permutes this eigenspaces. So just G maps the corresponding eigenspace corresponding to this formula on the characters. So, of course, so since there are finite number of this sets, so G acts by permutations by permutations. On the set of characters that appear here. So, on the set of characters that for which VK is not equal to 0. So and of course it permutes it, so you get a homomorphism from G to a symmetric group, so corresponding symmetric. So this is symmetric. And of course, if you think of, so you think of homomorphisms of G to some finite group, so of course the connected component should map to unit. So you get that G0 here, connected component, maps to the trivial element. For continuity, because the image of any element, so here you have finite number of elements, and in the finite set any element is open and closed simultaneously. So just any preimage of any element here is open and closed.
Is it so that there is a component, a specific component goes to unit element under this rule?
It could be, I mean, it is a component of a unit. Yeah, so there is precisely one component that contains unit. And this, so G0 is just, so G0 is component such a.
What is the component of unit?
So the component such that is contains unit.
It's connected component.
It is a connected component of the irreducible in the same time. So, and if you just map G to the finite group, just gamma, so finite. So let me state it explicitly. So this is, so points of gamma are open and closed subset and closed in the same time. So preimages phi inverse of gamma are open and closed. So they are unions of connected components. So unions of connected components. I'm just saying what is the real story here, but even this one won't be used actually. In the proof I do not use it, I just want to emphasize. So what we have so far, yes, so we are interested is follows. So you're having this vector in your space like I that sits in V. So of course G can act differently. I mean the set of characters that appear here as a derivative. So this is for the fixed character. Yes? So that we're interested in that realize the H as the stabilizer of this vector. So H is the stabilizer of the corresponding line. So now we have to stabilizing G of the corresponding projected line. So now we want to take our subset as small as possible. And but still G invariant. So what is the smallest G invariant subset? So of course, in order, and also you want V to be contained in such subset. So this is the following. So you have to take V. So let us take all the Vi and apply G to this collection of characters. So meaning that it is a sum of the elements G applied to chi. But this is just saying that it is a sum of V where G is applied in this way. And so here this, it is a sum in V, so it is clearly fixed. Okay? So this is fixed invariant subspace under G invariant subspace. I just use all pairs of elements. Yes, so G runs through all elements in the group. But it turns out that this sum is finite, where the sum is taken over the finite set of pairwise different characters. And so this sum is just some finite sum. And it is also direct. And so this is finite sum and direct of chi I not equal to chi j. And so you are picking up, so of course if you take a character act by G, it can act trivially, for example. Or it can just map the character in a few different equal characters, yes, so equal functions on H. But in the end of the day, you can take the representatives which correspond to different, completely different chi's. And this will be precisely this direct sum, because this will be the sum of such elements and it will be direct.
Show that it's a G invariant subset, I apply G EX, and show that it's a subset of V phi, right?
No, this is a subset of V.
To be a G invariant subset.
So, I mean, if you take it over all elements of G, it will be G invariant subset. Indeed, you act by G tilde. And this is the same as saying that this is G tilde G. And but this is equivalent of putting this to be equal to U. And if just it is U V chi, where you now, in order to write down G, it is just G tilde inverse times U. But if G runs all over elements of the group, U also runs over all elements of the group. So this means that this is an invariant subset, but then you look at which, so you know that you take the V chi and it maps to some other V chi, but they should map isomorphically because you have inverse, always inverse map, G inverse. You can apply G inverse, so they should map in. And this is just, so this is isomorphism, yeah, so this is isomorphism. So of course we have proved that G of V chi sits inside V of chi tilde, but since it is invertible, so since G is invertible, we can apply G inverse, you have isomorphism to V chi tilde to get to put inside V chi to the whole subset. Yeah? So this means that just you have picked invariant subset. And then we have to understand how this set can be characterized. So let us put.
I'm sorry, could we make a break?
Yes. Okay. So let us make a break. And, I shall explain how to derive out of this. How to realize H as a stabilizer as a subgroup in some linear. Okay.